In this video, we're going to be taking a look at a simulation of creating a sampling distribution. So again, the notion is that a sampling distribution is theoretical. We don't actually create these in the real practice of statistics, because it would consist of taking a sample statistic, so like a mean or a proportion of the sample, from every single possible simple random sample of the same size from the same population. And with sufficiently large populations, that would be a monumental undertaking, and so we don't actually create them. They tend to just exist in theory. But the interesting thing is that we know enough about the theoretical distributions to know how they behave. And so what we're going to be looking at here is actually an example of the Central Limit Theorem, which basically states that regardless of the underlying distribution of each sample, when we look at the sampling distribution for the sample mean for x bar, it turns out to have a normal distribution, which is really exciting to find out. We can use that to do a lot of things with inferential statistics. So let me tell you a little bit about what you're seeing here on the screen and how all of this is set up. This is a program called Fathom, which is a piece of statistical software. In this left-hand pane here, I have Fathom collecting some data from the U.S. Census Bureau. And what it's actually collecting here is it's taking a random sample of 30 individuals from the census, and it is plotting a histogram of their age. So down here, the variable on the x-axis is age, and on the y-axis we're looking at frequencies. So the heights are representing number of people in those different age brackets in the sample of 30 individuals. Then what the program is going to do, you'll be able to see the shape of the distribution from each individual sample in the left-hand pane. And then from that sample of 30, the program is going to calculate the mean age of that group of 30 and plot that mean over here in a histogram on the right, where it says mean age across the bottom and frequency of mean age. And as we collect more and more sample statistics, we'll be making a sampling distribution over here, and you can see what happens. So first, just to show you how the program works, I'm going to collect only one measure. It's going to take one random sample, compute the mean age, and plot that mean age over here. Okay, so here it goes. Here's our one random sample. It found the mean age of that group of 30 and it put it right here. Okay, so there's the mean age. And you can see that this particular individual sample does not have a normal distribution. This is essentially a unimodal skewed right distribution. I suppose it could be bimodal, but those aren't separated by very much. So unimodal or bimodal, skewed right. And there we have one single value. Just to show you what it does when we collect multiple measures, I'm going to collect 4 more. So it's going to take a sample, get the mean age, plot that over here. Take another sample, get the mean age, plot that over here. And it's going to do that 4 times. Okay, so here's a sample, mean age plot, sample mean age, and sample mean age. So we now have a total of 5 samples that we've taken. So 5 different x bars for 5 different samples. And you can see that so far this window isn't looking particularly interesting. Right now it actually looks like a uniform distribution with 2 gaps, right? But that's because we've only collected 5 samples. And again, a sampling distribution, a theoretical sampling distribution, is created by collecting x bars from, well, or any other type of sample statistic, but in this case we're looking at x bar, from every single simple random sample of the same size from the same population. So since we already have 5 over here, I'm going to collect 45 more. And again, you'll want to pay attention when this animation starts to run to the left-hand pane here, and you'll be able to see that none of these look normally distributed, but then you can watch what happens when we start to plot the x bars on the right-hand side. Okay, so here they come. And you'll notice it's far more likely for our x bars to end up kind of right here in the middle, and we're getting less of them off to the side, right? Less and less of them off to the side. And again, over here, very few of our samples have normal distributions for the sample. And yet you can see on the right-hand side over here with the sampling distribution, which is the collection of sample statistics for multiple samples, we're starting to get a normal shape. Okay, individual samples, not normally distributed, but when we take x bars from multiple samples and plot them, we're starting to see a normal distribution. And so this is going to keep running. It takes a little bit of time because we are actually asking it to collect quite a few measurements, and I do have the animation on. There we go. So now we have a total of 50, and even after 50, you can see we're starting to get a much more normal shape. Now what I really want to show you is, again, that's only 50 samples. That's not very many. I want to show you what would happen if we collected just a ton of samples. So I'm going to turn the animation off, otherwise this would take forever. We already collected 50, so I'm going to do 950 more. So there will be a grand total of 1,000 different samples that have been drawn. For each sample, the sample statistic, in this case x bar, representing the mean age, has been computed, and then all of those x bars have been plotted over here on the right hand side, and you'll be able to again observe what happens to this sampling distribution. So here it goes. This time it's not actually going to show us the animation, it's just going to tell us that it's collecting measures and let us know when it's finished. So here it goes, almost finished. And look at that. Look at how nice and normal that looks. Okay. If we were to allow the number of samples to tend toward that maximum, which would be all possible simple random samples of the same size from the same population, what we would see is that this would increasingly get more and more and more normally distributed. And furthermore, what's really fascinating and what the Central Limit Theorem actually says is that the mean of this sampling distribution will be the same as the population mean. Okay, so the sampling distribution mean age will be actually the same as the mean age of the population, and that the standard deviation of the sampling distribution for x bar is equal to the population standard deviation, whatever that happens to be, divided by the square root of the sample size. So without knowing what the individual samples look like at all, we can end up with a reasonable idea about the shape of the sampling distribution for x bar and the mean and standard deviation for that sampling distribution. And that's basically what the Central Limit Theorem says.